Physics 1 review, where we look at rotational motion. So in a nutshell, with rotational kinematics and rotational motion, the kinematic equations for rotational variables are the exact same as for linear/translational variables. You just swap out the variables, the linear/translational variables for the rotational variables. This equation right here is not on your equation sheet. These two are, however, it's not that hard to remember. You only have to remember it because its translational analog is on your equation sheet. So again, as a review of the variables, theta is angular displacement in radians. Omega is your angular velocity in radians per second. And alpha is your angular acceleration in radians per second squared. To get a translational variable from a rotational variable, you multiply the rotational variable by r, aka it's like you're just finding the arc length of a circle that's rolling. Okay, so theta times r gives you x, theta times omega, omega times r gives you v, and then alpha times r gives you a. Likewise, if you want to go from translational to rotational, you just divide the translational variables by r. And again, last equation right here is on equation sheet, but its its translational analog is, so you do not have to worry about memorizing it. Moment of inertia, it's the rotational analog of mass. It depends on the distribution of mass from the axis of rotation, which is a line about which your object rotates. The more mass is distributed from the axis of rotation, the higher the moment of inertia, which is what we see happening right here. The dumbbells are located further from this axis of rotation, this vertical line that rotates about. And the more mass is concentrated near the axis of rotation, the lower the moment of inertia, which is what we see happening right here. We have a lower moment of inertia, so our person has the mass is concentrated closer to the axis of rotation, so our person has a lower moment of inertia. For a system of point particles, we have that the moment of inertia is equal to the sum of the moment of inertia of all the point particles. So if we have a point particle M1, M2, and M3, the moment of inertia of the entire system is going to be sum of the moment of inertia of each individual body. The moment of inertia of an individual point particle is mr squared. So for example, right here, if this was a solar system of M1, M2, and M3, the moment of inertia of the solar system would be M1 times R2, R1 squared, plus M2 times R2 squared, plus M3 times R3 squared. Okay? A big point to make known is that the distance, r refers to the distance from the axis of rotation, that vertical line, in this case for our person. It does not refer to a specific center point. Since we can't rotate about a center, we always rotate about a line. Okay? Newton's second law and torque. Okay, so torque is the rotational analog of force. It's caused by a force acting at a distance r from an axis of rotation, where theta is the angle between the force and the radius. So, a force can act but not cause a torque. That can happen if our force acts at the axis of rotation, meaning r is equal to 0, or it can not enact the torque if the force is parallel to the radial line that it acts along, meaning that the angle between the force and the radius it acts along is 0 degrees, and hence sine of 0 is 0. The same relationship between moment of inertia and angular acceleration for a given torque as between mass and acceleration occurs. So, the same way that we have A equals net force divided by mass, we have angular acceleration equals net torque divided by moment of inertia. So if we have a larger moment of inertia, in this case A, where mass is concentrated around a rim, an applied force at the edge will cause the same amount of torque in both cases, but less angular acceleration in this case because the moment of inertia is higher. Whereas in this case, the angular acceleration will be higher for a given torque because the moment of inertia is lower as the mass is concentrated at the center. So torque visualization right here is that we draw our radial line that our force acts along. We draw our force starting at the radial line and protruding outward. And then our angle theta occurs between the force and the nearest part of the radial line. So in this case, theta would be between these two parts, whereas if theta was, say, to protrude outward like this, theta would be between the force F protruding outward like this and this part of the radial line right here. So theta would be right here, if you can visualize that in your head. Center of mass, the single point that is representative of where all physics for an object occurs. In the absence of a pivot point about which to rotate, an object subjected to a net torque will always rotate about center of mass. For a collection of point particles, okay, the center of mass is what we call a weighted average. So what that means is instead of just adding all the masses together and dividing by m, what we do is we take the masses and we take the individual mass and multiply it by its location, x, meaning that we're assigning importance to that mass through its position. Then we sum together the mass multiplied by its position for each particle and then divide by total mass. So in this case right here, if we had m1 assigned to position x1, m2 to x2, m3, x3, and so on and so forth, we would have m1 times x1 plus m2 times x2 plus m3 times x3 plus so on and so forth divided by the total mass m of the system. And to hit on the prior two bullet points that were brought before, if we throw a wrench in the air, the wrench has more mass concentrated towards head, so the center of mass will be about right here, which is why you'll see a wrench rotate around this point right here, closer to the head, as opposed to being at the center of the wrench. So that's why you'll get that weird and wonky rotation instead of a nice, smooth, symmetrical rotation, and that's because the weird and wonky rotation is natural to the center of mass. So we have some new conditions for equilibrium. The still old conditions that we used from Unit 2 are still prevalent, meaning there's zero net force, zero acceleration, corresponding to a constant velocity, dynamic equilibrium, or at rest, static equilibrium. However, in addition, now the net torque must also be zero. Okay? In this case, we can have net force can be zero, but net torque can still exist. Or we can have that the net torque is zero, but there's still a net force acting. So let's look at both of those cases. Okay, so in this case right here, we have that our net force is equal to 2F. Okay, so we're not in equilibrium, but our net torque is equal to zero because the force acting right here is acting in the counterclockwise direction, while a force acting right here induces a torque in the clockwise direction. So we're not in equilibrium overall here, despite the fact that our net torque is zero. In the second case, we're also not in net equilibrium, even though our net force is equal to zero. We have a force of F acting downward and a force of F acting upward, so our net force is equal to zero. However, our net torque is now equal to F times L because we have two forces acting in the counterclockwise direction at equal radii, L over 2. So as a result, we're going to have F times L over 2 for our torque right here, F times L over 2 for our torque right here. When you add that together, it gives you a net torque of FL. So translational versus rotational motion. If an object rolls, it has rotational motion in addition to translational. And you must include for the term for rotational kinetic energy and energy problems. It'll pop up here in a second. K equals 1/2 I omega squared. There are two principal factors that affect the degree to which an object rolls. Friction. Friction increases angular acceleration and reduces linear acceleration. The idea being that an object rolls when friction acts on it because friction enacts a torque at this point which causes your object to start rolling and accelerating. So if friction increases, your angular acceleration will increase, but your linear acceleration will decrease. Similarly, friction converts potential energy into rotational kinetic energy. So as a result, if friction increases, that means that more energy is going to be diverted to rotating and hence rotational kinetic energy, and that's going to reduce your translational kinetic energy. The other factor is the moment of inertia. The moment of inertia for different objects is always different. It's not the same as mass. We can have two objects of the same mass that have different moments of inertia. So as a result, the larger the moment of inertia for an object, the larger the rotational kinetic energy. And then again, here's our energy term now with the rotational kinetic energy term thrown in. Lastly, we look at conservation of angular momentum. If no external torque is acting on a system, angular momentum in the system is conserved. Li equals Lf. I initial times I omega equals I final times omega final. For a conserved amount of angular momentum L, there exists an inverse relationship between the moment of inertia I and the angular speed. This is demonstrated right here. As we saw in class with the person sitting on the stool with the dumbbell, it also happens with roller skaters, or ice skaters, excuse me. If an ice skater hangs their arms out wide like this, um, they'll be rotating with a small angular velocity. Since angular momentum is conserved, if they bring their arms in, they're decreasing their moment of inertia, so as a result, their angular velocity will subsequently increase. In some cases, such as Kepler's second law, angular momentum can be conserved while linear momentum is not. The force acting does not cause a torque, and we'll go over that when we get to Unit 8. And lastly, if working with mathematical problems involving angular momentum, it's useful to know that the angular momentum for a point particle is mvr. And that covers day 7.